Okay, so good morning and good afternoon or good evening to everybody on the call today. Thank you for joining us to learn more about all of the latest developments with AI-powered engineering with SimScale. So my name is Alex. I'll be hosting today's session, and I'm very pleased to introduce our speakers, Steve Lene and Ian Pegler. I'll briefly introduce both of them and then we'll get started. So Steve is the Application Engineering and Partnerships Manager at SimScale. He's based in the UK. He has a technical foundation with a master's degree in mechanical engineering and a PhD in materials science. Steve has 7 years of industry-relevant experience, ranging from working in aerospace design to engineering simulation. We're also very pleased today to introduce Ian from NVIDIA. He is the Global Business Development Manager for CAE, and he's a seasoned CFD engineer with 12 years of experience, holding a master's in aerospace engineering from University of Southampton. He's now based in Chicago, and he's part of NVIDIA's CAE team, driving developer relations and business development. Outside of work, he enjoys running, programming, and skiing. Now, before we get started, I'd just like to remind everybody that all audience members will be muted on entry to the session. However, we hope that you can all hear us okay. Please let us know if there are any problems with the chat. Also like to remind everybody that you can ask questions in the chat as we go along. We'd love to see your questions popping up there. We'll have time at the end to address those, and of course, we'll also be able to follow up with you afterwards. So without further ado, I'd like to hand over to the presenters. Steve, I think you are going to kick things off for us today. So the floor is yours.
Perfect. Thanks, Alex. So yeah, first of all, I'd like to give a very short introduction to SimScale, and then Ian will give us a short introduction to NVIDIA and the technology that's being used today. And then we'll get into the details of this exciting foundation model that we've released for pump design, including, of course, some live demos of this capability in SimScale. So first of all, welcome everyone, and I'd like to introduce SimScale first. So we're an established simulation company. SimScale runs entirely in the web browser, in the cloud, so you'll see that during the demos. And we have about 600,000 users worldwide now across 50 plus countries. There's millions of simulations being run all the time in SimScale, and we're top of the leaderboards for G2 reviews for our software. So if you don't already know who we are, go and check out simscale.com and you can sign up and give it a try. And what do we do? Well, our ethos is to empower engineers to innovate faster. And we do this by providing a high fidelity simulation tool that's truly accessible at any scale. You can see across the bottom of the screen some of the organizations that we work with. Many more, of course, we're not allowed to mention, but Rimac Automobili, the Croatian hypercar manufacturer, is doing just this. They're empowering their engineers to innovate faster by using SimScale. In the early stage in the design process, the designers are iterating very quickly through cooling channel designs using SimScale's platform. So just another couple of overview points on SimScale, and then we'll get into the NVIDIA side. So SimScale is finding a lot of success in the industry by reducing simulation lead time. And we're doing this by an order of magnitude. Thanks to the differentiators of SimScale being completely cloud native, so you don't need any local HPC or hardware to run simulations. Because SimScale is fully hosted in the cloud, it's very easy to collaborate. So wherever you are geographically, you're logging into the same cloud servers when you share a project and accessing the same data. This means that you can simulate across borders without having to transfer large data sets. SimScale is completely scalable, so you can run really large simulations, you can run a lot of them in parallel, but that scales with your needs. So maybe today all I want to do is run a simple FEA linear analysis. When I submit that, a small machine in the cloud will be started, maybe a 4-core machine. But then tomorrow, maybe I want to run 1,000 conjugate heat transfer CFD simulations in parallel. I can do that without having to switch on any special license. I have that capability at my fingertips. So we have a broad physics capability as well. You can do thermal, structural, CFD, and electromagnetic simulations all in one simple, easy to use interface. And of course, all of that can be used to train AI models and surrogate models to get more than 100 times speed up in your simulation and maintain the access control and visibility through the organization of those AI models. And we'll show that in the demonstrations. Okay, that's the introduction to SimScale. I'd like to hand over to Ian now.
Great, thanks Steve for the introduction. So I'm just going to give a quick introduction to how NVIDIA helps enable computer-aided engineering to go faster. So we go to the next slide. Kind of this gives an overview of what NVIDIA does. Fundamentally, we're an accelerated computing company. So we want to take what people do today and just make it go faster, be that computer-aided engineering, AI, any task, we want to accelerate that. And we do that by building a platform for accelerated computing, which is, at the bottom level, fundamentally the hardware that you're all familiar with, the GPUs, but we also produce a lot of different other components as well to enable the GPU, like our networking solutions. And then obviously there's the hardware itself, the current Blackwell generation of GPUs. And then sitting on top of that is probably our kind of secret sauce really is, which is all of the kind of software libraries that enable our development partners such as SimScale to kind of build these kind of awesome solutions. So, CUDA, and then a whole range of other libraries to enable different use cases. So if we move to the next slide. And why do we do this? And what are we trying to achieve when it comes to computer-aided engineering? Well, ultimately, the story, I think, over the last few years of computer-aided engineering is we want to do things faster, right? I mean, back when everything was testing based, you could potentially do, one test a week of a design variant. And then obviously computer-aided engineering came along and we could quickly start to simulate these kind of physical tests and maybe do one a day. And then with accelerated computing using GPUs, we can start to do even more different iterations today. And now with AI approaches, potentially we can run, 17,000 different iterations of a design a day. So what it allows us to do is obviously hopefully make a better, cheaper product, because we can just look at so many more different variations. So that's what we're really trying to enable, right? This revolution in engineering design to really improve the design in a much shorter time scale. So if we move to the next slide. This kind of gives an overview of some of those libraries that kind of sit on top of our hardware that really help developers produce these accelerated tools, such as what SimScale have done. So I won't go through them all, but you can kind of see, some of them are to help with some fundamental mathematics. And the one I want to point out really is PhysicsNeMo, which is the second one in there. And so this is like a library that helps build AI models to simulate the physical world, basically, and we call it PhysicsNeMo. And there's, if you want to know more, obviously, our GTC just happened, and there's a lot more information you can find out about all of these different tools and libraries if you go and visit the GTC website. So we move on to the next slide. Then specifically when it comes to computer-aided engineering, how can we help accelerate that? So, we just spoke about PhysicsNeMo, but there's also a ton of other libraries and tools that we use So CUDA, obviously, most people might be familiar with that. This is the way that you can kind of program for the GPU. Then we have obviously PhysicsNeMo to generate the physics-based AI models. Then Omniverse is a kind of platform that allows people to create digital twins and bring different data together to create this digital twin experience. But the key thing I always say to people is the key thing to remember about NVIDIA is we are a platform company. You know, we don't make tools. We build this platform for SimScale to build their tools on to take advantage of this underlying technology. So that's why I'm super happy to be here today to kind of showcase what SimScale have put together using PhysicsNeMo into their platform. So if we move to the next slide, this is a little bit more about PhysicsNeMo. So this, like I said, is our library of different AI architectures, basically that to help with traditionally computer-aided engineering problems, right? So, we've done use cases that cover all of these different application areas. So, actually, on the right there, cooling system design. If you look closely, you might be able to see that looks like a GPU in a computer, and this is really where kind of PhysicsNeMo came from. Some of our own needs to actually cool our own hardware, and then we developed it into a library that other people can use as well. And one of the great things, obviously, about PhysicsNeMo is, it's not supposed to be a replacement for any traditional CAE, but hopefully it's a way to kind of, like we said earlier, iterate faster and get more design iterations assessed, and hopefully give you a better design at the end of the day. So if we move on to the next slide. And I like this slide because it kind of shows perfectly how SimScale have leveraged the kind of some of the NVIDIA tools to build what Steve will show you in some of the demos that he's going to show after me. So, taking some of the underlying tools that we have, so PhysicsNeMo, this framework, and the domino architecture that you see on the left there, and integrated that to create the underlying pump foundation model, and then integrating that into the SimScale platform to make it easy for you guys to use. And obviously, we also you see a nice animation there of actually the pump as well, done using the Omniverse APIs. And if you'd seen the SimScale actual GTC keynote session, you would have actually seen this video as part of the keynote session as well. So just shows you how we can help take some of the visualization stuff to kind of the next level with some of the photorealistic rendering and bringing all this kind of CAE data into one place. So with that, hopefully that gives you a bit of an introduction to how NVIDIA helps accelerate computer-aided engineering, and particularly how SimScale have leveraged some of these platforms to kind of help build this awesome pump model that's now integrated into their platform. So to get to more details of that, I'll kind of hand it back to Steve to take you through.
Perfect. Thanks for that overview, Ian. It's really insightful. So what we're going to talk about now is, exactly what we built and how we built it to deliver this pump foundation model. And also a bit of information on our strategy for AI in SimScale. So ideally, what we're aiming for here is a situation where you can say, design me a pump that achieves these requirements, has this pressure head, is the most efficient possible pump, pumps this type of fluid, and is this type of pump design. So in order to do this, we need to take a bit of a step back and understand the challenges in engineering, and also how AI is being implemented in engineering today. So I'm sure all of you are familiar with some of these tools, and engineering is already being revolutionized by AI. Things like copywriting are being revolutionized with the use of LLMs and prompting. It's very easy to improve the readability of some text or do some background research. Also, for image design, it's very easy to generate images that are royalty-free and show some of the specifics that you want to show for certain products or types of engineering. And also coding, especially for people that don't code every day, the use of IDEs with embedded AI algorithms and LLMs are really helping to generate code and debug issues in code as well. So these things are all proven technology and they're already well adopted in the engineering industry. But when it comes to the core engineering, so the design and simulation process, things are not so well integrated yet with AI. We're still using parameters from CAD, creating traditional geometries, be it BREP or implicit style geometries, and then sharing that with separate teams or into separate pieces of software to run simulation setups, generate simulation results, and then loop back through to change the CAD and go through that loop again. So the steps between CAD engineering and CAE are fairly disconnected. There's no universal data type. And crucially, there's no large public data sets available to train these things on. So it's relatively slow and costly to evaluate it. One of the great things about the internet is it provided a huge source of data for LLMs to learn from. But engineering data is typically intellectual property and it's not published widely for people to use to train AI. So we had this thing come up a few weeks ago. It was actually Alex that came up with this idea, and I thought it was a great thing to cover today on the differences between using an image prompt to actually doing engineering with AI. So here we have an image, and we prepared this image by asking for 3 surfers paddling out to a wave, or some surfers paddling out to a wave with 3 surfers on the wave. And it looks all right initially, but then when you start to look at the image, you realize there's some errors on here. So one person doesn't have a surfboard, people at the back don't have faces. It's clearly an AI generated image. But that's not a problem when you're generating an image, because you just prompt it again, and there's plenty of tokens available for new images to be created, and you get multiple variations very quickly. And in the end, one of these images will be acceptable for what you need. So in this circumstance, it took 5 generations of an image before we had what we wanted. Everything here looks physical. There's nothing wild going on. There's nobody without a surfboard. It looks sensible. But in order to do this with engineering processes, we have to be a bit more methodical. You can't just keep reprompting when you get an incorrect result, because you might not know straight away that it's an incorrect result. So in order to address this, in SimScale, we have 2 approaches right now. We're covering engineering and agentic AI, as well as physics AI. So physics AI and engineering AI are going to be working alongside each other to solve the same sort of problems. And first of all, I'm going to focus on the physics AI. This is the application where we've developed a foundation model with NVIDIA PhysicsNeMo for the pump situation. Then at the end, we're going to also look at the engineering agentic AI process and how this can all be pulled together with an AI agent to simplify the workflow. So let's think now about how we build a foundation model. And with the status quo today, if you want to create an AI model, what do you have to do to generate that? Well, the first thing is the data generation. You need to get your data in order. You need to collate that from different sources. You need to prepare it so that it's ready for AI. That might mean tagging. It might mean rerunning simulations. And then you need to prepare the AI model training. You need to have an infrastructure to manage that. And you may also need to have the same simulations available that we use to train the AI as well, because when you do an AI prediction, you may not be happy with the results that you get back from it, and you might want to be able to use the PDE solver technology as an alternative. So this is the process, and what we're hearing from the industry is that, it sounds great, but I don't necessarily have time to invest in creating this training data, or I'm waiting for the right project to come along that will give me enough data to train on. Or how do I know if it will produce sensible results for my application? The great thing about doing this on SimScale is we have an end-to-end solution that meets all of these requirements. The other great thing is you don't have to know today that you definitely want to implement AI. Just by using SimScale, you're preparing your data ready for using AI in the future. Every time you run a simulation on SimScale, the data is stored and cataloged in a way that it can be used in the future as an AI training data set. We save all simulation data, and that's very different to traditional SPDM processes for saving data, because in that scenario, you would only store the output result for maybe the PDF and the input parameters. You usually don't store the actual simulation file, and that's what you would need to train an AI model in the future. So with SimScale, you get all of that. So we're getting to the point now of the foundation model. And what is the foundation model? Well, what we've done in this first example is we've created a foundation model for a pump. And this is basically a pre-trained AI model. You can take it today and you can use it on your pump designs. And it gives you insights straight away, potentially. But the other fantastic thing about having a foundation model is it creates a base level, a base camp that you can use in order to create a highly customized AI model for your data. So we've already trained the foundation model that understands the physics of how pumps work. It knows what blades do. It knows what a number of blades being changed does. It knows about the outlet and the inlet. And then if you take that baseline and you add in another 50 so of your simulations on your specific pump designs, you'll then have a highly tailored AI model that can predict the performance of your pumps. So the idea here is we think that this should help to reduce the barrier to entry on AI projects. And this is the first example that we've produced, and we're going to produce many more of these foundation models in collaboration with NVIDIA. So let's look at the foundation model for pump simulations specifically in a bit more detail now. So what we've done is we've created a large data set of pump models with a huge number of geometry variations and different operating points. All of this comes together into a simulation data set that has thousands of simulations in it. So this is the great thing about us making this available, because we've done a lot of the hard work to prepare this foundation model. It can basically be a training model that you use in the future for your own one, as I described. So we took that large data set and then we used NVIDIA PhysicsNeMo to create an AI model, a graph neural network AI model, to be able to make pump predictions. You can use this through the UI, as I'll show you, but you can also use it to make instantaneous predictions of what the result would be for something like an optimization. And this is one of the really exciting applications that we're seeing AI models being useful for. A traditional optimization study may take days or weeks to complete because you're fairly limited in how parallel those simulations can be, because you're reliant on the previous simulation finishing and the results of that simulation to inform the optimization algorithm what it can do next. But if that simulation is an AI model and it takes 1/3 of a second to complete, you can iterate much faster through those optimizations, and you can do a real-time optimization. So that's one of the things we did with this foundation model, is we ran a optimization study so that we could explore a design space in real time. So the points you see being generated on the plot here can actually be generated in the same amount of time that you see them being generated here. We ran a optimization study here of 300 designs. They ran in batches of 20, so we parallelized 20 at a time. And the total optimization took less than 5 minutes to run. And you can see how we're optimizing for efficiency versus pressure increase for this pump. And after each batch of predictions, the geometry is changed in order to hone in on the optimum efficiency area that you see in the top right of the plot. So you can obtain this within about 5 minutes, which is obviously ridiculously fast. And then you know the parameter space of interest for the operating regime. And then you can investigate this in more detail with full simulation to validate the results or use physical testing. Okay, so that's a bit about the background. And now I want to show you some demonstrations of how this actually works in SimScale and how we make this a reality. So for the first demonstration, I'm going to show you an example of how we set up the CAD geometries for the actual generation of the data for this foundation model. So I'm going to show you how this works in Onshape. This can obviously be done with any CAD tool. This can be generated using Siemens NX, Creo, CATIA, whatever CAD tool you're using can be used as the input geometry for generating a foundation model. So we created many different CAD models by parameterizing them, and you can see here the parameters that we can change, and I'll show you how this works through the UI. But obviously, in reality, this would all be driven via a script through the API. So if I change the settings that we have here, you can see the geometry changing. So if we change the number of blades to a much higher number, we'll see the number of blades generated increase drastically. And this is just how we build up the parameter set. And then obviously we're using a genetic algorithm or another way of iterating through all of these different CAD designs by changing the parameters that you see here, including things like scaling as well, so that we can understand how different sized pumps are going to respond, and as well the diffuser angle and diffuser length. So we're looking not only at the impeller, but also the volute, the type of pump, the diffuser, and this is just one of the pump geometries. We had many different pump geometries that were parameterized in this way to create the data set. Okay, so then that's for the geometry generation. The second demonstration I want to have a look at now is how we can actually execute this programmatically and create the data set. So in reality, there isn't very much to show here. I've got a very short video here which shows the number of lines required to actually generate hundreds of simulation ready data sets from one of those parameterized models. So I really don't like showing code in a demo, so this is the only time I'll show any. But this is an example of what you need. So we're running 200 in parallel in this case, and then 600 in total. And rather than showing the rest of that video, I'll show you live in the platform what we have here. So here's an example of some of the pump data sets that we've used for this foundation model. You can see a wide variety of different pumps, but you'll notice some similarity as well. For the foundation model at the moment, the inlet always has to be aligned with the same cardinal axis. The outlet always has to be in the same direction. The rotating region has to be centered around the origin, and that's about the extent of the limitations. So long as your pump complies with those geometric limitations, then you will be able to predict the performance of it using the foundation model. So here's an example of the data set that was generated. This is from one of the DOE runs. We can see one of the pump results here on the screen, and we can see this project contains 211. So there's a huge number of these pump simulations, and they range from taking about 30 minutes per simulation run. So this one ran in 31 minutes. I think the one at the bottom was slightly quicker. Yeah, that one ran in about 15 minutes. And the important thing to note here is that these are parallelized. So we ran batches here of about 200 in parallel. So within a day, you can generate thousands of simulations with SimScale. So it's really powerful to be able to leverage the capabilities of the cloud infrastructure to be able to generate these data sets for foundation models or AI models in a very short amount of time compared to how long it would take to generate these sorts of data sets with traditional on-premise tools. Okay, so we've gone from generating the CAD through to now the simulation data. So once we've done that, then we're ready to start training. So the third point here is how we actually train the model. So I'm going to show you, as I mentioned at the start, SimScale has an end-to-end process. We don't need to go out to any clunky tools in order to create the training data or clean the data. Everything is integrated into one end-to-end solution. So in order for me to train a new model, all I need to do is visit simscale.com and go to my dashboard and start setting it up. So as an admin of SimScale, I can control who has AI training permissions. So that's available in the dashboard. I have that permission, so I can go from here and I can create a new AI model very easily. So I'll say pump example here, and I can give it a description. Then I go to start the training, and this is where I then go to select the data that I want to use. So in this circumstance, I'm just going to navigate to an area that we have for all of these pump foundation models. And I'll use one of these projects as an example for the training. Obviously, for the foundation model, we used all of the projects that are available here to cover a very wide data set for all of these pumps. And this process is something that can be done by any engineer in the organization. It doesn't need to be something that the expert machine learning team does. It's very accessible straight in the browser, so you can add the projects that you want to use and set up the different parameters for your training directly here. So you can see this project contains 500 runs. I confirm that I want to use those for my model, and then I just give it some information. Now, the important thing about training AI models is you're always going to have different versions, because you create the first version, train that, and then undoubtedly in a week or two's time, you'll have some more data. And the great thing is this model can always be developed and learning with you. As you have more data to add into it, you just retrain it with additional data. So now I start training this model, and it's literally as easy as that. I'll get a notification in a couple of hours once this is finished training. Right now it's being submitted to be trained in the cloud on some NVIDIA GPUs, and then I'll have it available and I'll be able to publish it and share it. The only other thing I would do right now is I would set up the documentation for it so that my colleagues know how to use this model when it gets published. And then once it's available, I can come in and publish it out to the team. So that leads me on to the fourth part of the demonstration, is once we've trained this model, then how we deploy it to the organization, and also how we use it, both via the graphical user interface and the API. Okay, so the last point then is how we then deploy this within the organization. So what I'll do is go to the AI model training section and show one of the example foundation pump models. You can see this one's had fairly extensive use, about 4,000 runs so far. And here we can see it's in the released state. And if it wasn't released, I would just go here and click release, and then I would make this available to the organization. I can see the details of the regression analysis that was performed during the training here as well. So I can just verify the results that I've got and then publish this out to the organization. So let's have a look how we would actually use this in the UI. So in order to do that, I'm going to create a new project here, and we'll populate that with some CAD models, and then we can do some predictions. So create a new simulation project. And then I'm going to import some CAD geometries in here that I want to simulate. So I'm going to do this by populating this from a template where I've already got some pump geometries that we can use. So here I've got one geometry. You can see it's a centrifugal pump. The inlet is aligned with the Z direction, the outlet is aligned with the X direction, and the rotating region, the impeller, is rotating counterclockwise around the Z direction. So that meets the requirements of the foundation model. So I can go and switch on the foundation model here now to get a prediction of what the performance of this pump will be. You can see it literally takes a few seconds to load in the UI. We're already getting a prediction of the efficiency and the scalar values that we're expecting to get out of here. So we get the forces and moments and the pressure increase produced by the pump, and the efficiency. So it takes a few seconds more to do this through the UI than it does via the API. It takes less than a second via the API. And that's obviously for one geometry. It's very easy to interact with the result and see how it works. And we can also bring in many other geometries as well. So I'll show another example now as well. We'll have a look at a different geometry, completely different pump, much larger impeller, completely different volute design. See, the inlet is still aligned with the Z direction, the outlet aligned with the X direction. And again, we can see the prediction of the performance along with the key metrics that we want to get out. So let's just show one more. It gets a bit samey after doing a couple, but let's just show an example of one more result here. Another different geometry, the same geometry that I showed the parameterization of actually. And again, in a few seconds, we get the performance predicted on the CAD geometry. So you can see how this can be used really quickly to iterate through different designs. I've mostly showed CAD changes here because I think that is the nicest thing to show, but of course I can make changes to the boundary conditions as well and predict the performance based upon that. Again, I'll get an instantaneous prediction of the performance from a boundary condition change. And the beauty of this is this can all be driven through the API as well. So this can be integrated into an optimization algorithm or into other workflows, integrated into a control system called from another tool. The opportunities here are endless with integrations through our open API. Okay, so that's what I wanted to show from a demonstration point of view. Now, in order to talk about how all of this gets tied together, there's one last thing that I want to go through, and that's how agentic engineering AI can augment this together and automate the manual processes that are usually done by an engineer for something like this. So we have a full version available of this now that works as an AI agent that removes the manual setup requirements and simulation work needed to actually prepare a geometry, set up the simulation, and then do an optimization study. So how the engineering AI runs in SimScale is it's an AI agent that you talk to just like an LLM inside the SimScale platform. We're using a RAG LLM for this and chat code through a form completion service. And we can use our vast array of data to train this on all of the public data that's available, because we have over 600,000 community users in SimScale that are simulating every day, uploading geometries, and we can use that rich source of data in order to train our LLM service. So let's have a look at how this actually works. And this ties together everything we've just talked about with the AI foundation model, the use of templates, running PhysicsNeMo in the background to make predictions, and also run an optimization study. So let's have a look how this actually works in this example. So here the user is talking to an AI agent directly in the platform, and they've uploaded the requirements PDF for an RFP for a pump. The chatbot can then identify using an LLM in the background what the requirements are in there. So it can see that the required pressure head is 10 bars, and then it can set up the simulation using a pump template in SimScale. So it knows the tree structure that's required, and then it can prompt the user if there's anything missing. So in this circumstance, the rotation velocity was missing, the rotation speed of the impeller, and the user just prompts it to say, yes, that's 1,500 RPM. And then the AI agent says, well, actually, there's a foundation pump model available in SimScale that would meet these requirements. Should we use this to predict the performance? So the user accepts that, and then we actually go through to the process of the AI agent helping to run an optimization study. So here it's set up an optimization study and identified using that foundation pump model the region of interest for optimal performance. And then obviously as a next step, we may want to run a validation CFD result and interrogate that in more detail. So you can ask things like, is there cavitation occurring in this design? The agent will then check, make sure that there's no pressure below the vapor pressure and confirm that there wouldn't be any cavitation. It can do further processes like run the final validation simulation run and also do things like produce the final PDF report. You know, all CFD engineers love simulating but hate doing the final report. Why not automate that process and have all of the simulation results produced in that PDF report automatically at the end? Okay, so that's the final demonstration. Just as an overview of what we've seen, SimScale provides a fast path to mature physics AI and agentic engineering AI. You can get instant simulation predictions in the UI and also run instant optimizations as well, thanks to the end-to-end process that we've implemented for AI. Also, we want to make this as open source as possible. We want to invite you to see what you can do. So as a participant of this webinar, we will make available to you a Colab script. Now, I really don't like demoing script, so I didn't show you the script live today, but the whole process for running the optimization study has been published in a Google Colab script, and you can pick that up and run that very easily, and then you can replicate exactly what you saw here today. We'll provide a Onshape pump model. If you don't already have access to Onshape, you can create a community account, and we've published this pump model as a community available model, so you don't need a paid Onshape account to access that. We will grant everyone who's interested access to SimScale for a couple of weeks with a professional license to be able to run this pump foundation model and evaluate the performance of PhysicsNeMo live in your browser. Okay, thank you very much for your attention. We're on time, so be very happy to answer any questions.
Thank you very much, Steve and Ian. Great presentations, and very nice to see a live demonstration always as well. We've actually had a few questions. Quite a few came in just in the last few minutes. So I'm still going through them. I guess I'll start with maybe one that I missed at the beginning. I should have said that this webinar will be available as an on-demand session once it's processed in maybe a couple of days' time. So look out for that on our website, and please do share it with your colleagues. So then I'll get into maybe the more technical questions that we've got here. So, gosh, and they're still coming in. So, maybe one about the training data. Often people ask how much training data do I need to maybe create one of these models, or how much training data was used to create this model?
Yeah, it's a really good question. Whenever we show something like this, we always get asked how much training data is required. Now, the answer to that really depends on the use case. So with this foundation model, we wanted it to be as broadly applicable as possible. So we needed a very large training data set. This model has around 4,000 simulations in it. So it's one of the bigger training data sets. And we're also going to keep building on that and adding more simulations into it as we have them available. For a more focused use case, if you wanted to build your own AI model and you weren't actually building a foundation model, you need, depending on the number of boundary conditions, depending on the number of geometries and the extent of the parameter space that you're looking at, you need something in the region of 50 to 200 simulations. And as I mentioned during the demo, this isn't something that is likely to be static. You may create a first AI model that meets your current requirements, but then as your designs change over time, you may go into a different parameter space where your AI model is no longer suitable. So you may need to run a few more simulations and add them back into the training data. But that's the great thing about the model. It can learn and develop as your designs develop.
Great, thanks. Maybe this one's a question for you, Ian. It was about the hardware that's used, like what sort of hardware is actually needed to generate or execute these kinds of models.
Yeah, that's a good question. So, I mean, one nice thing about what we do with our GPUs, right, and our whole ecosystem is like pretty much CUDA will run on any GPU. So what hardware depends really on like the scale of the problem and you know how quickly you want to actually solve the problem. But I guess one nice thing about doing this with SimScale is you don't really have to worry about that. Those guys kind of take care of that for you. So I would say it depends on your needs. So, but it's one nice thing, like I say, is you can play around with anything you want on our GPUs, from the smallest, from the cheapest card all the way to running on like our data center cards, like the Blackwell generation. So yeah, sorry that I can't be more specific, but yeah, it just really depends on how quickly you need to turn things around.
Great. Then there's also a question about applications. So particularly if this is using some data from the SimScale community, can we then produce predictions for other kinds of CFD problems like aerodynamics, hydrodynamics?
Yeah, of course. So PhysicsNeMo and our whole AI implementation strategy is physics agnostic. So you saw in Ian's slide the vast array of problems that PhysicsNeMo can be applicable to, from weather patterns through to geological data, additive manufacturing. In SimScale, whatever you can simulate in the platform, you can train an AI model on.
Great. Is there an option to pick up results that are actually created from other simulation tools and use them in this kind of workflow?
Yeah, of course, that's a question we get a lot. So can we use legacy data? So out of the box with SimScale, the easiest thing is to use SimScale data that has been generated on SimScale. But we can obviously run services projects to assist with migrating legacy data and making that available for training AI models as well.
Thanks. Another one here about the agentic AI demo. Question is whether that's already available in the platform, or what was it a preview?
Yeah, that's an eagle-eyed participant noticed my only non-live demo. So everything else was demoed live. The agentic AI is available. It's currently on our development server, and I wasn't brave enough to demo something that's on our development server live today. But so yeah, what you saw in this presentation was a preview, and it will be released very soon with the capabilities that you saw.
So it's coming. That's very exciting. Okay, I'm just having a look to see if there are any others that we can address right now. So there was a question about how to produce the data set in the first place. So in this case, for the foundation pump model, how did we check the results that the results of each simulation were actually reasonable? So how difficult was it to find mesh settings that converged well for all of the different pumps we ran?
Yeah, it's a really good question, actually. In this circumstance, we're using our multi-purpose solver, which is a very robust solver. We chose mesh settings that were fine enough that we shouldn't have issues with all of the different CAD geometries that were generated. We have quite a robust automatic mesher. Obviously, there can still be problems. So we did have to remove any failed simulations, and that is done automatically in the training process. So when I showed the AI training process, there's an option to automatically exclude outliers from the data set. So those are automatically removed when you do the training. But there is obviously some rigor that needs to go into the setup. We had situations where we generated geometries that had faults in them, and then they didn't necessarily work. So you do have to make sure at the start you're using a good simulation setup. You run some mesh convergence studies to make sure on the breadth of different CADs that you're going to get, you're going to have a converged simulation result. And then make sure that the setup is robust to all of the changes. So there is some rigor that needs to go into it, but we have a robust end-to-end process to generate that data.
Sure. So the next question is, I think you touched on it a little bit during the demo, but how long does it take to train the model, and what happens if your training data set is very large? I think the question here is if it's sort of 80 gigabytes per run, maybe.
Okay, yeah, it's a good question. Really, the amount of time it takes to train depends on the data set. So I've trained some AI models in SimScale that were fairly small. They ran in a couple of hours on a GPU in our cloud infrastructure. However, for much larger models such as this one, it typically takes an overnight run to train the model. And you don't need to worry about storage, file size. We take care of all of that in the background in our cloud service.
So is it more a function of the number of individual runs rather than necessarily the model size in each case?
Yeah, I think it's a function of both. So larger simulations obviously require more data and are going to take longer to process. But from what I've seen, it's the number of simulations that has the biggest impact on the time it takes. And
sure.
The whole process is automated. As you saw, it was very easy for me to set it off. We automatically reserve a portion of the results to be used in the training, in the regression analysis, and they're used as unseen data points. And the model is constantly tested against those during the training. So the bigger the data set, the more training data is segregated to be used as unseen models.
Great, thanks. And maybe we've got time to squeeze one more in. There was a question about whether we can include the piping, it's sort of upstream and downstream inlet and distribution system in addition to just the pump itself in this kind of project.
Of course, yes. So this model that we've trained, it's focused on the pump itself, but you could obviously have the downstream and upstream pipes connected to it as well, and you could train a model on that.
Great. Okay. I think there are a couple of questions still that we probably don't have time to get to since we're right at the top of the hour. So I'm going to stop there. We can follow up with those questions afterwards. So what it leaves me to say is thank you very much to both of our presenters here today and for everybody in the audience for joining us. I think we've all learned a lot about some exciting new technology which is coming along. So thank you for that. And I'll say until next time, goodbye.
Great. Thanks, Alex. Thanks, Ian.
Thanks.
Bye.